Okay, everybody, welcome back. I hope you all had a good break, whether you're watching us on site there in Vilnius or you're watching us online from all over the world. It is my very great pleasure to welcome to our Jupyter virtual stage here. Our next speaker is someone who has been kind of pushing the boundaries of .NET and open source and C# since I got involved with it. I think I first met Oren at a open spaces alt.net event, which has got to be coming up for 15 years ago now.
Yeah.
He's worked on so much stuff that I've used, that my teams have used, RavenDB, Hibernate, all kinds of things. And today he is going to be telling us how to build a database from the ground up. Please, folks, welcome to the Build Stuff virtual stage, Oren Eini.
Hey, thank you for having me, and thank you for everyone in the audience. I want to tell you about how to build a database, and I want to tell you how to build a database when we start from effectively find your project. Now, please don't try databases. This is a very important lesson that I would start out. They are complex, they will take years of your life, and you will be a competitor to me. Don't do that. More seriously, I spent the past 13 years or so building RavenDB. I've built multiple database engine, distributed queues, all sorts of stuff for a long time. And I spend a lot of time just trying to think about what would be the best thing to do. I have about 45 minutes. This is a really dense topic. I have to go on low-level details and jump around in the stack to make sense. If you have any questions, please ask them as you think about them. That would make it much easier for me to remember what I'm talking about. And I hope that we'll be able to cover lots of grounds here. So the first thing that we have to understand is that I don't actually care about the data model at the storage level. At the storage level, if you're using relational or document model, column family, graph, everything about it is more or less the same. Now, it's interesting to note that the choice of the data model can have an impact on the way that you're utilizing your storage. For example, if you're using Postgres, then you know that there is vacuum and there is the TXID wraparound and all sorts of stuff like that. And those are conceptually bugs in the overall implementation, because you have to be aware of how the data is actually stored and managed in order to make efficient use of this. Most storage engines, you really don't care about those low-level details. What I'm looking at is OLTP scenarios, online transaction processing. So if we have lots of reads, lots of writes of relatively small values, where we care about the individual values. This is in contrast to OLAP, online analytical processing, where you're typically doing updates on batches, you're writing reports, queries, and this is a whole different topics that has its own details. Now, let's talk about what we actually need. We need to store and retrieve data, and data from my perspective is some blob. I don't care about its format, I don't care about its shape, and none of that matters. Now, if you're using a relational database, you know, there is a schema to the data, and sometimes this is the way that the database lay out the data on disk, and it matters for certain optimization. It doesn't really matter for the level in which I'm working. What matters is that we're storing and retrieving certain blobs, and then we want to do operations on them. So we want to get some data by key, but what is a key? Is it some arbitrary value that I give you? Is it the primary key that the user assigned? What about if I want to do a search on the data? What about if I want to scan through the records based on some concept? How does indexes relates to that, all of that? And it turns out that the query language, the way that you do that, doesn't actually matter. In the end, all database has to deal with those questions. How do I store the data on disk? How am I able to iterate over that? How am I able to find a particular record? And it's interesting because in many cases, if you're used to, oh, I'm writing SQL, I know I have to do indexes, you're working at a very high level of the database at the conceptual level, but it ends up that this is also almost one-to-one mapping on how you do that at the bottom. And we're going to start building things from the bottom up. So the first thing that I want to discuss is that you absolutely require, if you build a database, it should be an ACID database. ACID, atomic, consistent, isolated DO. Basically means that you have transactions that you can modify multiple values at the same time in an atomic manner, that if you put the plug, the data is safe. Now, you may choose to not implement transactions, in which case you have a dumpster file and not a database. Now, there are some cases in which I'm going to say, okay, great, you have made an explicit choice to be a main memory database. Memcache, Redis, there's MemSQL, there's a whole bunch of databases that have made this decision. They are operationally complex to manage. They don't, in my estimation, they make things a lot harder because you can't do a lot of stuff. And they also get away with cheating a lot because, oh, we're running on memory. If you have large database, get a lot of memory, that makes your performance much easier. We are talking about, okay, no, I have to actually persist data to disk. I have to do that in a manner that is safe. So let's talk now in detail. How am I actually going to store the data to disk? Now, sometimes if you build a database, you're going to say, hey, just give me a partition or give me some block device, and I would move on from there. It used to be the case that Oracle, SQL, you would, for best performance, you would go and use that. If you're using a database on a file system, that you also have to deal with all of the niceties that the file system provides. And when using niceties in the Chinese terms, where they make you sit on top of a growing bamboo, and then you get to experience the beautiful sensation of nature in its raw form. So the problem is that if I'm storing data as a file, as a block device, something like that, how do I deal with data modification? Let's assume that this is my data, and I'm going to write some data here. And then I need to update that. So I need to write another line here, but there is also some other data here. So I need to, now I have a free space problem, a disk allocation. Where do I put data? How do I move it around? And if you're think about the simplest database possible, a CSV file. I want to go to a 2 GB CSV file, and I want to change the name of the first user. I want to add a space to that. This is a 1 byte change to the record. But because of the format of the CSV file, this is 2 GB of data that I need to modify. This is untenable. This is not something that you can actually do. Most databases has the concept of pages. And this is actually, I'm not sure where the term pages come from, probably from something like this, because I have all of the pages in my my database, in the file, in the block storage, etc., and I can modify each page independently. So that's interesting because the cost in terms of I/O, the cost of modifying a page is effectively fixed. If you think about how it works with SSD drives today, then they have blocks, and the blocks is typically 4 KB in size, and you cannot modify anything less than that. Practically speaking, it means that the cost of updating 1 byte or 4 KB is exactly the same. And in terms of I/O, and that means that if we treat the data in page sizes, and we always modify the data in page sizes, that gives us a lot of benefit, because it means that, okay, I can load the page, and any modification that I do within this page boundary is effectively free. So I modify this line or this line, doesn't matter. I can rearrange the shape of the page any which way that I want. It also means that now all of my data is scoped to a page. If I have a piece of data that is larger than a page, I need to allocate multiple continuous pages in order to store that. Most databases have pages in 4 kilobyte to 4 megabyte. The 8 kilobyte, 16 kilobyte range seems to be the most popular one that we are talking about. Now, let's talk about how do we manage free space. And remember, at this point, I'm assuming that I have a partition, I have a file, and I'm managing everything. I don't, what I'm asking from the operating system, from the file system, is give me a block of data on disk and stay the hell away from me as much as possible. This also plays very well to the manner in which you're working with the operating system, the file system. You're not going to talk to the file system, okay, I want to write a page here, a page there, increment the size of the file one page at a time. That can be horrendously expensive. Instead, you're going to pre-allocate, probably at a range of, let's say, 128 megabyte each time that you allocate, and then use and use and use over and again. So that means that I now allocated, let's say, a file whose size is 128 megabyte, and now I need to start operating on that. But now I need to track myself what pages are free, what pages are busy, all sorts of stuff like that. I can do that through a bitmap. But where is that bitmap going to sit? And the answer to that, it's going to sit as the first value in as the first page or the first pages in the data file. Now that is interesting. Look at those numbers. An 8 kilobyte page where every bit is this page is used or not used. Notice that I'm using pages a lot. This is a bit recursive. This is a bit recursive. So we have in an 8 kilobyte page, we have 65,000 bits, which map to about 512 megabyte. So we can say that, okay, every time that the size that we have, we're going to, so every bitmap page that we have can allocate, can manage a space for 512 megabyte. I'm going to state that for simplicity of operations, we're going to dedicate 8 pages at the beginning of the file to manage the free space. Why 8 pages? Because that gives me 4 gigabytes in which to work with. That leads to an interesting observation. If we're operating in a block device, then we can assume that the value is fixed. The size of the size of the block that we have is fixed. We can allocate the bitmap at a known size, and we're good. There is no need. There is no concept of allocating more space. However, now we are running in the area of the cloud where I can literally go to a block device and says, okay, let's give it another 100 gigabyte or something like that. And in many cases, I'm running on files. So I can just say, oh, let's increase the size of the file. If I increase the size of the file, I need to change the size of the bitmap. And if I'm putting that in the beginning, then I already wrote data after the bitmap, so that's complex. So I'm specifically focusing on that just to give you, because the bitmap and the free space is a relatively simple scenario that I can cover that would explain some of the issues that you run into when you're working with pages for data processing. There is another aspect of why I might want to allocate for a file and a bitmap for every 4 gigabyte. And the answer for that is that what happens when you delete data? Let's assume that I now written, I don't know, 100 gigabytes of data. And now I started deleting all of the data. What happens then? Well, if I'm storing the information as a single file, it's kind of hard for me to return the DSpace back to the operating system. There are advanced API that allow you to say, okay, this section in the middle of the file, let's give it back to the operating system. You can do that. It's really, really, really not advisable to do that. It's an advanced operation. It opens you up to all sorts of edge cases of what happens if I'm running near maximum disk utilization. I have a hole in my data file. I'm trying to write to it, and it's really hard to understand whatever I can allocate this space, not allocate this space. Am I actually going to? Basically, it's hard. There's too many edge cases that you have to deal with. So if you're saying, no, my database is actually composed of many 4 GB files, whenever you create a new file, you're going to say, oh, I'm just going to allocate the fixed size bitmap at the beginning. And this frees you from having to deal with bitmap reallocations and stuff like that. It also means that if the entire file is empty, you can just delete the file. And that frees the disk space in a predictable, no fancy APIs, no nothing that you have to account for. One of the interesting things that you discover when you start building databases is that kernel, file systems, hardware will all lie to you, will all cheat, they all have bugs. You will run into them in nasty situations. So saying, okay, let's go and use some API that isn't bog standard, boring, has been beaten and stressed, and all of the bugs have been squeezed out for decades and decades. This is not something that is acceptable, because you will run into those issues. And again, punch a hole in the file. What happened when you run out of disk space? It is an interesting problem. It also relates to some of the considerations you have to make. How am I going to operate over my database, not through my database itself? I shut down my service and now I want to zip the files. I want to send them over using rsync. All of those things are things that you have to consider when you consider the wider ecosystem. So this is basically what we just talked about. File every 4 GB, you can simpler to return the space. There is a downside on the other hand. If I'm talking about a file every 4 GB, then at 4 TB, I might be hitting this limit. Now, that is an interesting problem because, okay, I have a 4 TB file, 4 TB database. Probably I can afford to have the admin raise that limit. But this is something that you have to be aware of, because when you start running into this issue, it would probably be a critical error. So consider the scenario where you are running for 2 years and very slowly you're reaching the point where you're close to the magic limit, and suddenly hit it, and suddenly everything just start failing because you have critical failures. You can no longer open files. Another thing to consider is how are you going to deal with the directory structure? You can throw all of the data into a single directory, and that's possible, and I wouldn't recommend that. It is a typical database would actually be composed of multiple different files. Even if you're going to a single data file, you're going to have some headers, you're going to have the transaction logs, you're going to have a whole bunch of stuff like that, temporary files that you may need. And especially if you're going with multiple independent files, I would say that you want to create a nested directory structure. So you would have a /data directory that contains all of the data files, /journal directory that contains all the transaction logs, things like that. And even for the data files, you may have, there is this notion in some database that called file groups. So all of the files that belongs to a particular group are under a particular directory. Now, why do you want to do that? It's And the answer to that is that if you throw that into separate directories, you can now use the operating system capabilities to store that on multiple independent devices. And this is just something that you can do. You can do that in an incremental fashion. This is not something that you have to build on your own. This is something that you can lean on the operating system to do. And that's absolutely something that you want to be able to utilize, because that can be quite hard to do on your own, because I have this custom theme that is almost never used, but sometimes it is, so sometimes forget about it and it works, and then I have a bug and a bunch of other stuff like that. So if you use a nested directory structure, you can drop that responsibility to the file system level, to the operating system level, and you're freed from worrying about this. Now, as a database author, I care a lot about I/O, because I/O is so slow. I cannot express how slow it is. And so you cannot just read and write directly from the device that you're using. That is also true if you're using SSD. That is also true if you're using NVMe. That is still true if you're using non-volatile memory and all of those sort of things. Why? Because there is this very clear memory hierarchy. And even if you think about it, even at the CPU level, if you write in high performance code, then you care about register versus L1, L2, L3, and main memory. And even then you have NUMA nodes, non-NUMA nodes, non-local, a bunch of other stuff that you have to worry about. This is when you're talking about memory. When you talk about storage devices in the cloud, the actual storage may be remote. So basically slow. So how do you handle that? You have to have some form of buffering. Now, this has been a really hot research topic for a very long time. There is this TQ algorithm, and this is a really good discussion of that. And I love that algorithm because it's simple. It's, I don't know, like 50 lines of code to get the gist of that, and this blog post explained it beautifully. But again, now we have two additional problems. Now we manage the memory, which means that we have to be aware of who is using the memory. Now, it means that we have a chance to do all sorts of really nice optimizations, but at the same time, we have to take upon ourselves quite a lot of stuff to do. The other side is that, let's say that I'm running read-only operation on a particular set of pages. So what I'm actually doing, let's say that I'm accessing this page in many concurrent transactions, read transactions. Now, what do I have to do for each one of those read transactions? I have to access this page. I have to increment a ref counter, and that can create a hotspot just in the sense of I now have contention on the ref counter. And it sounds silly to worry about that when I have the cost of going to disk, but it turns out that in many cases, after you've done all of this work of buffer management and you figure out what the working set is, most of your work is in memory. So suddenly this becomes a noticeable hotspot. An alternative to doing that is to say, oh, well, I'm just going to map the whole thing to memory. And from this point on, I'm not going to worry about the I/O. I can just do memory map. The kernel is going to page things for me. The kernel is also going to handle things such as buffering, buffer management, swapping to disk, all sorts of stuff like that. That's a lot of code that you don't have to write. What's even more interesting is that the kernel in many cases can have a global view of what is required from the system. Now, the downside of that is that you don't control the I/O. And for writes, you sort of can, because you can do file I/O, and that should be sufficient for most cases. For reads, you access a piece of memory and you have a page fault, and that stops the thread. Now you can do things such as, okay, use mincore, prefetch the data and stuff like that, but that is quite complex. Now this becomes harder to deal with if you're using memory map files and concurrency, because you may have locks. Now, if you are holding the locks while you're hitting a page fault, you may be holding that lock for a very long time. That's something that you have to be aware of. But let's talk about concurrency in general here. We absolutely want concurrent transactions. The question is whatever we want concurrent writers. Now, if you have concurrent writers, you have to use locks. There is this great paper called OLTP Behind the Looking Glass, and it analyzes common OLTP databases and try to figure out what are the relevant costs. 40% of relational databases cost performance goes around lock management. That's absolutely insane. You also have to write a lot more tricky code in order to deal with that. So we're going to go with a single writer model. The single writer model sounds like, wait, this is a problem, but it turns out to be not that much. RocksDB, LevelDB, NMDB, RavenDB, all of those have the single writer model. All of them have mitigations around how I can still get some level of concurrency while not having to deal with, oh, I have multiple threads modifying the same records and I have to somehow deal with that. There is also another interesting detail that you can have here. It is possible to have multiple single writers. And what is multiple single writers? This is when you can divide your database into a distinct sections. For example, you may have the data and indexes that are stored in such a way that there are no concurrency between them. You may have, I don't know, different tables, and you're guaranteeing that the single writer per table, and you're still able to create cross-table transactions because you only have to synchronize the commit state, not the intermediate state between. So the question is, what is the scope of a single writer? You can have it on the whole system on a particular file. This is when a file per file group or per table, something like that. The idea here is that you can have concurrency on those independent scopes, and the lock is very coarse, which means that you don't really need to manage the locks all that often. And that can be a huge benefit. Now, just to give you some ideas, I can get on a Raspberry Pi using a single writer, I can get upward of 10,000 writes per second, 20,000 writes per second. On standard cloud machine, I can hit 150,000 writes per second using a single thread. In most cases, this is not something that you actually care about. But I mention that because this is something that people keep bringing up. Now, there is another level of concurrency that we have to think about, and this is readers and writers. How do we handle that? And I don't want reader and writer to block one another. So there is a methodology called multi-versioning concurrency control, MVCC. And one nice way of doing that is called copy on write. Whenever I need to modify this page, I'm not modifying the page in place. I'm copying that page to the side and I'm modifying it here. Read transactions are going to go and update here and look here, and they are not going to be bothered by whatever changes I'm making here. The key aspect is that I can use something called a page translation table. When I commit the data, I can say, oh, whenever you need page number 5, don't go to this version, go to this version. And this gives me an atomic switch between transactions. This gives me the ability to have multiple versions of the same page and the same values at the same time. Only when all of the transactions that are looking at that are closed will I actually copy that value from the temporary memory into the data file, and then I can discard that and remove that from the page translation table. This is basically doing a switcheroo behind the scenes, and it is an extremely elegant way to handle concurrency and multiple versions at the same time. What about durability? I have to deal with power loss, with crashes at the operating system level, at the application database level. I have to deal with someone pull the plug, literally pull the USB stick from the system. So if I'm talking about storing the data as a memory map file, this is a problem. I don't control when it gets stored to disk, and I don't control in what order this is done. This is done by the operating system. Even if I'm using file IO, unless I'm calling fsync, I haven't set when the data is going to actually be recorded. And you end up with some really, really strange scenarios, because you may be writing, let's say that I'm writing a megabyte to disk, and I'm done writing this megabyte, and then I'm calling fsync, and then I crash in the middle of fsync. What would you expect this to happen? And the answer is that in this case, the answer is that I have absolutely no idea. The state of the system on the disk is unknown. It is possible that I started writing and I started the first few pages are the new value, everything is old. It is possible that they're intermixed, old, new, old, new, old, new, and everything in between. So you can't count on any of those. But go back and remember that we have the page translation tables. That means that we are tracking which pages we modify. When we commit a transaction, we're going to take all of the modified pages and write them to the journal. And we're going to do that in a persistent manner. So we're going to use these flags. On Windows, we're going to use file flag write to and file flag no buffering. And those are basically the same. That forces the file system to throw that all the way to the block device. It sends it to the block device with a flag called FUA, force unit access, which basically means store it to persistent data and don't come back to me unless this is persistent. Now, using a journal is a really, really interesting optimization, because we have sequential IO, which is fast, really, really fast. Random IO can be extremely slow, even on SSD, and sequential IO is always fast because it has always been fast, and this is what people are optimizing for. So on restart, I can go back to the journal and start reading each transaction in turn and writing the modified pages from the journal to the disk, and in this way I recover the transaction. Notice that everything that I just explained here is quite trivial. You have this thing, you have the modified pages, and you write them to the journal, and then you just write them from the journal to the data file on recovery, and you have an ACID system. So everything that I just spoke about was almost the bare bone of what we're doing. Let's talk about how we are actually going to store the data itself. So we have pages, but we won't, okay, so I can read the page, load the page, I can do that with transactions. Yay, what's going on now? So let's talk about some basic operation. I can put some data, get some data, and have this notion of ID. An ID gives me O1 access to the file, to the data. Now, the ID is basically an offset in the file. That's it. There's nothing more beyond that we need to deal with. If the value is too big, then we have multiple pages. One page, multiple pages to store that. What happens if the value is small? In this case, I have the notion of slotted page. This is an 8 kilobyte page. And I'm going to start writing the values from the top down. Value number 1, number 2, number 3. At the bottom of the page, I'm going to store the indexes to those values. Now, why does it matter? It matters because now I can store the small ID is the position here. What does it matter? It matters because now I can look at the ID and I'm going to say, okay, if this is an ID that is at the beginning of the page, then I know that this is a large ID and I can use that. If this ID points to the middle of the page, then I know this is an offset to the position of the value in the page. So this is a small ID, and then I can jump from here to here. Remember that just loading the page is a single unit. So jumping from here to here is a cheap operation. At the same time, it means that I get stable IDs. What does it mean, stable IDs? Let's say that I'm deleting number 2. So I have some gap here. I may want to defrag this page. I might want to move a value true to the top. I would have to put here 0 or some marker here, and then modify this to be 7021. So the ID that I have still points to this guy. And this small level of indirection means that I can defrag the internal space inside of a page without having to change the ID. Now, let's talk about what am I actually doing with that. There are 2 common ways for you to organize data inside of a database. First of all, you have this thing where you actually store the data. But then you need to actually access that according to something. I mean, yeah, I can give you the offset into the data and you can probably do something with that, but you probably want to be able to query on that using some other property or field. So in here, we have the notion for B+Trees and extendable hash tables. Both of them, by the way, are older than me. The first mention of the B+Tree is from the, I think, early 70s, late 60s. And then it was already called ubiquitous. And the basic idea is that you have a page, and the page point to nested page, and everything in here is about a single, a set of values. Now, if you're familiar with a binary tree, you know that this is a O log 2 of n search space. A B+Tree allows you to, instead of having a branching factor of 2, has a branching factor that is much higher than that, typically hundreds of entries per page. Now, this matters because that means that when I'm searching on the B-tree, I can go from here to here, and I only had 2 disk accesses to handle that. Another thing that you would typically see in B-trees is that you have the key, and the value is this offset. So this would be the kind of B-tree that points to a different location. Now, a B-tree is a sorted structure, which means that you get lookup by key that is very efficient, O log n, and you have also all sorts of interesting behavior around iteration. So you can ask questions, okay, give me all of the users from Margaret and onward, or give me all of the orders after 2019, stuff like that. That gives you order iteration that can be really, really important for processing queries. The other thing that you have is extendable hash table. And I spent a lot of time thinking of how you can implement hash table on persistent storage. Everything that I did was extremely complex and unworkable. And then I read the paper on extendable hash tables, and it was like, wow, this is amazing. This is a really beautiful scenario. The idea with extendable hash table is that this allows you to have O1 access with all of the usual benefits of that. And regardless of the data size, you can do a lookup by key, but all of the downside as well. no order iteration, no ability to do sorts or seeks or any of those sort of things. Almost all cases, you do not want to implement this. You want to go with a B+Tree. That's almost always the best thing. And why is it almost better? Because hashing only gives you data by key. The B+Tree gives you by key, by a prefix, which is also important, by order iteration, stuff like that. You can have a key that is actually compound. Think about the phone book, where the primary key and the starter that you have is last name and first name. This is a compound key, and you can use a prefix. Give me all of the users whose name is whose last name is Smith. So it's very easy to do that. So the B+Tree is effectively a tree, has a value which is the key, and the value can be either the ID of the document, which means that we have to do another lookup, or we can store additional values in line inside the B+Tree. That can be very useful if you want to answer the data directly from the index. In general, I tend to prefer smaller is better. The smaller your data size is, the more packed you can make the B+Tree, the easier it is to store all of that in memory. You can also do some really, really fun things with compressions. So there is something called HOP, which is a order preserving compression. And that can give you a reduction of 80+% in the density of your B+Trees without actually sacrificing anything else. But I don't know if you notice, I'm trying to cover quite a lot of ground on a limited amount of time. Those are the main highlights that you have to take into account when you want to store when you want to build a storage engine. On top of this, now you start thinking about, okay, how am I going to build the actual database? So let's say that I'm talking about, okay, I want to build a relational database. So I'm going to say, okay, I'm going to define the schema. I'm going to define the way that I'm serializing a particular row into a blob. Then I'm going to store that into the database. And I'm going to define indexes that allow me to fetch the data in this manner. This is how any relational database works, basically. If you say, oh, I want to actually have a graph database, then, oh, wait, I need O1 access time. That's what the internal ID gives me. I need to be able to do point queries. So maybe I'm going to store that as a B+Tree that gives me all of the related values, things like that. Some interesting resources that I want to cover. Designing data-intensive applications is really good coverage from the top down. How can I use databases and data storage systems in order to solve problems? And I think this is a great book because it covers what are the use cases. The database internals book goes the other way around. This is how I implement those sort of details. Both of them tends to be a bit high level, roughly not to the level that I was speaking right now, but something similar to that. I also wrote this book. This is about 400 pages. This is going to take you into the process of writing a storage engine from a new project, including all of the code that is relevant to write it, how you manage buffers, how you manage the journal, transactions, all of those sort of things. And now it's time for questions.
Okay, so we have one question in the chat here, which is from Gitis Respecta. Do you have some suggestions on implementing efficient distributed table partitioning? It is certainly not great in vanilla PostgreSQL. brackets, expecting it to be totally transparent to the client. Nice, easy one to start you off.
Yeah. Have you stopped beating your wife? That's the kind of, so here's the problem. If you want to, so everything that I just spoke about refers to a database that is running on a single node. If you want to talk about distributed systems, you have to start talking about how do you manage the failure modes. Because if I could ignore the failure modes, I could give you this answer very quickly, and it would be a wonderful system indeed. The problem is, what happens when I have a partition in the system? What happens if a node goes down? What happens if one node has, out of this space, it's still up, it's still running, still saying, okay, but it can't accept any more writes. So you have to consider all of those details. I can tell you that in many cases for databases that are not natively distributed, the answers are pretty sucky. The typical scenario for Postgres, for example, would be to have a primary and secondaries that are replicating on top of the primary operations, but that gives you gap. If you want to do partitioning, and let's consider what does partitioning means. Well, it means that you split data. So you might actually have multiple B-trees that are, let's say that the classic example is to have an orders table and it is partitioned by year. So you're going to have a separate B-tree on a per year basis. But if you want to do that on a distributed environment, well, that's a different issue. What are you actually going to have to do here? Well, what you have to have some agreement about which data resides where. How do you handle where some of the nodes are inaccessible? All sorts of other stuff like that. The short answer that this is a really complex problem. And in many cases, the reason this is complex is that at the database level, you're trying to solve a very generic problem. But at the application level, you can make a lot more assumptions, and that can dramatically reduce the complexity that you have to deal with.
Okay.
Yeah.
Great stuff. All right, I don't see any other questions in chat. So the way this works, folks, there will be a Zoom link dropped in on PineTool, and Oren, I'll drop that into the Zoom chat. Head on over there. There may be some more folks have some questions or things that they want to chat about. Thank you so much, Oren, for taking the time to share your insight and wisdom with us today. I love the intro there. Here's how to make databases. Don't make databases.
But, you will lose a lot of sleep.
No, it's always one of the things I love about events like this is getting a chance to really kind of get an insight into stuff that a lot of us don't get to work on, day to day in what we really do. So, Oren, thank you so much for sharing that. Thank you, folks, for tuning in. We're going to drop that Zoom link in now. So if anyone wants to continue the conversation, hit that link, head on over and continue it there. Otherwise, we're going to take a short break and we'll see you back here in a few minutes. Thanks for tuning in, folks. Have a good one.